Hi everybody. Today I'm going to quickly go through how to complete lab number 3, regression and statistical analysis. And this is our intro lab to doing regressions. We're doing simple regressions here. The next lab we're going to bring in multiple regression analysis. And we've talked about this a lot and we've looked at it in class a lot, but I wanted to make sure to give you all an opportunity to see how to go through and do it. And so I'm going to switch the view in just a second and show you how to do it on my Stata program. So let's get started. Okay, so I've got my Stata here, and the first thing I want to do is begin the log, and so I'm going to name it with my name and the date, or maybe I'm going to call it my last name and lab number 3, and put it somewhere where I'll be able to find it. And then make this a little bit smaller. And then the first step in the lab is to, if you want to, open a do file. Again, that's always something you can do where you can save notes for yourself and save commands for yourself and things that you've done that you want to do again, especially as you start to get into more complex coding. It's a really useful tool. I'm not going to do it today because I am pretty comfortable with the data, the commands we'll be using. But what I am going to do is go ahead and import our first data set, which is that home price data set. And again, all these data sets you can get from, you can download them all from Coop, or you can go ahead and get them from the Canvas site for our class. So I'll go ahead and upload that. And you can see that it uploaded perfectly. There's the command import Excel with the file name and then the comma, which sheet page to use, and the first row as label names. And so, you know, in the good old days, you could actually just type these commands in, like log using, etc. I can see all my variables there. And the first thing I want to do is summarize the data set. So I'm just going to call that for my own notes, part A. And then I just want to summarize all of the data. And so I've got the descriptive statistics for all of the data. And when that more comes up, it just means it's not done calculating all of our summary statistics. And then the next thing I want to do is run a regression of sale price on lot size. And so I can go ahead and do reg sale price, lot size, and get my results. And here we should be pretty familiar with these results now. We can talk about our point estimate, our estimated coefficient beta hat, the standard error, our p-value is nice and low, our confidence interval does not contain zeros, so we can reject the null hypothesis at the 95% confidence interval or the 5% significance level. And so what I want to do is interpret the coefficient beta hat and then interpret and describe the confidence interval. So I'm going to go ahead and say the estimated coefficient for lot size implies that each additional square foot of lot size will tend to increase house sale price by $6.60. And I'm rounding up because that's the logical way we would deal with that number if it's money, right? We don't say $6.59.88. That's illogical. The important things here are we're talking about a marginal change in X, and then the beta hat is the size of the effect on Y. And it's important that we talk about how it's not 100%, right? It tends to be. We think it's generally this. It's more or less this. We don't know for a fact, but we're 95% sure it's pretty close to that. And that's the next thing we can say. We can say that a 95% confidence interval of 5.722 9, let's say 23 or 7.2 to 7.47 tells means we are 95% confident that the true value of beta falls between $5.72, and $7.47. This also implies that we can reject the null hypothesis that beta equals 0 because the confidence interval does not contain 0. Sound good? So now we've interpreted the coefficient. We've talked about the confidence interval. We can also want to remember, like it says there, the coefficient beta hat is interpreted as the effect of a marginal change in x on y. The effect of marginal change in x has on y. And then we want to run a regression of sale price on bedrooms and interpret the beta and the confidence interval and compare the two R-squareds. So we want to remember the R-squared for lot size is 0.287, telling us that our model explains about 28.7% of the variation in sale price. Now I can run a regression of sale price on bedrooms, and I get a new coefficient. This coefficient tells me that each additional bedroom tends to add $13,269.98 to the sale price of a house. We want to talk about the confidence interval and then talk about the R-squareds. The confidence interval tells us that the true value of beta is most likely between $10,432.31 and $107.65. We can be 95% certain that the true beta falls within this interval and is non-zero. The R-squared for the regression of sale price on bedrooms is 0.13. Excuse me, I apologize, 1343. Meaning this model explains approximately 13% of the variation in sale price. The previous regression model explained about, was it 27% or 28%? This implies that lot size is a better indicator of sale price than bedrooms. Oops. Forgot my little asterisk. There we go. Oops, still forgot my little asterisks. There it is. Woo! All right, that's it for that data set. Now I want to go ahead and clear that out. And now I want to import the forest loss data set and take a look at what we have there. Again, I want to remember to import the first row as variable names, and then I want to start by calculating the descriptive statistics. So I'm going to summarize the data set, see that everything shows up there, and then I'm going to run a regression of population density on forest loss, this time generating a 99% confidence interval. So I'm going to regress forest loss on pop dens, and the confidence interval is going to be 99% this time. So now I'm much more confident that the true value of this beta, this coefficient, is non-zero and falls between 0.00053 and 0.001. So if we want to interpret the confidence interval for the beta hat and the confidence interval for this problem, we can go ahead and you can reference the book for this to get the units, because the units on this one are a little bit more challenging. But the basic thing here is that each additional person per hectare is going to tend to increase deforestation by 0.00008. So our marginal change in X is, per 1,000 hectares. That's not how you spell hectare. Nope, that's not how you spell hectares. Will tend to increase forest loss by 0.0008%. We are 99% confident that the true value of beta falls within the confidence interval listed above. And you can go ahead and list it out. I'm not going to spend a lot of time typing here today. Confidence interval above. We can reject the null hypothesis. And then we want to go ahead and interpret the R-squared. And again, remember, the R-squared is talking about the model. And this is the model. When we add in other explanatory variables, they'll pop in here, and that'll be part of the model. But the model is basically everything on the other side of the equal sign from y. And that's what's explaining variation in y. So our model tends to explain 43.45% of the variation in forest loss. And then the last regression we want to do is regression of population density and crop change, and see what we get from there. And we get some weird results here. We get a really low R-squared. We get a negative coefficient telling us that a marginal increase in crop change is going to tend to decrease population density. And we get some other stuff we don't like. We get a really high p-value. We get a 95% confidence interval that definitely contains 0. So this tells us that crop change, which is a change in the amount of cropland in a given country, is not a very good indicator of changes in population density. So that's what you want to say, is you want to say that the 95% confidence interval and the p, both imply that we cannot reject the null hypothesis. A marginal increase in cropland will tend to decrease the number of people per 1,000 hectares by 11, but we can't be confident about the explanatory power of this model. The R-squared implies that our model explains about 1% of the variation in population density, and we cannot reject the null hypothesis that R squared is 0 because the p-value for the F statistic is large relative to the significance level of 0.05. So basically, this is not a good model, right? The p-value is much higher than 0.05. The F statistic is very low. The R squared is very low. The adjusted R squared is low. This contains 0 a lot. And it's a very wide confidence interval, too. It's not terribly narrow. And the p-value for the t-stat is very high. And here's another thing. If you look at that coefficient of -10, crop change increasing is going to decrease population density. The standard error is also 10, and that means that our coefficient has an error that's equivalent to the size of the effect. So that's like if I said, well, I think that getting an A in the class is going to increase your wages by $1, but I might be off by $1. Right? If the size of the effect that I'm predicting is equal to the size of my error term, that's not a good sign. So this is basically a bad regression, and we're probably not very confident with our results. So we can say as part C, the results much stronger than those of crop change on population density. Oops. And then I would not use crop change to explain variation in population density in the future. Cool. And then I can go ahead and close my log. And I'm done. So that's it. Hopefully that helped. Let me know what questions you have. Have a great rest of the day, and I'll see y'all next time. Thank you.